Why do wind turbine blades almost always have 3? Wouldn't using 2 blades be cheaper and spin faster? Actually, while 2 blades are cheaper, their unstable rotation creates severe vibrations, putting immense stress on the tower. So what about using 4 or 5 blades? Although it rotates more smoothly, the additional weight and manufacturing cost are not economical. Therefore, 3 blades represent the golden balance point between performance and cost. Of course, this ingenious design is not solely reflected in the number of blades. If we zoom in closely, we can observe that the airfoil of each individual blade is specifically engineered. It gradually thins from the root to the tip. The thicker root is responsible for maintaining structural strength, while the thinner tip is designed to enhance both speed and lift. This design effectively minimizes wind resistance. When wind passes over them, the air velocity above and below the blades differs. The resulting pressure differential is the core power driving the hub's rotation. Furthermore, each blade has a distinct twist angle from root to tip. This is because different parts of the blade move at varying speeds. The further from the center, the faster the rotation. If this twisting isn't done, the airflow at the high-speed rotating tip would become turbulent and messy, causing severe vibrations, even snapping the blades. Additionally, to ensure the blades always face the wind, an anemometer and wind vane are installed at the very back of the nacelle's top, which constantly monitor the wind's speed and direction. Once the wind direction shifts, the wind vane instantly sends a signal to the computer, which then activates the yaw motor positioned at the tower's top. This motor powers a massive ring gear, rotating the entire 300-ton nacelle. Through this precise movement, the nacelle can consistently keep its blades facing directly into the wind, thereby ensuring that every single bit of wind energy is fully captured. At the center of the blades is the hub, connecting 3 giant blades all securely bolted onto it. Inside the hub is a large electric motor, responsible for rotating the blades along their axis to precisely adjust their angle. Immediately behind the hub is the nacelle. The first core component inside the nacelle is a solid steel shaft connected to the hub. When the wind moves the blades, the main shaft slowly rotates along with them, transmitting power into the nacelle. Although its torque is substantial, it only rotates 15 revolutions per minute. This rotational speed is far too slow to generate electricity directly. Therefore, a gearbox is connected right after the main shaft. Its function is to significantly increase the speed, boosting the rotation from 15 revolutions per minute directly to over 1500. Subsequently, the power then enters the high-speed shaft. Due to its extremely high speed, it's also equipped with a hydraulic braking system. If extreme weather like storms occurs, massive hydraulic calipers quickly lock the high-speed shaft's brake disc, preventing the blades from spinning out of control. Finally, the high-speed shaft connects directly to the machine's crucial generator. Inside it are 2 core components, the rotor that spins with the shaft and the stationary stator. When the rotor spins rapidly within the stator, mechanical energy transforms into a steady flow of electricity. The generator's output frequency is directly tied to its rotational speed. For instance, in a typical 4-pole generator, to meet our national grid's 50 Hz standard, the rotor must maintain a constant speed of 1,500 revolutions per minute. But the problem is that wind power constantly changes. If the wind is weak and the rotation speed drops to 1200 RPM, the output frequency will become chaotic. If the deviation is too great, it could damage electrical devices or even cause widespread blackouts. Since wind speed can't be fixed, what can we do? This is where the doubly fed system comes in. The principle behind it is this: a control system injects an additional current into the rotor coil, which then generates an independent magnetic field that compensates for any speed deviations. You can think of it as a dynamic compensation for discrepancies. Ideally, when the rotor spins at exactly 1500 RPM, it can then precisely output 50 Hz. If the wind drops, the rotor speed falls to 1400 RPM and the output frequency is only 46.7 Hz. Then the controller will immediately add a 3.3 Hz difference, and when combined, it's still exactly 50 Hz. Conversely, if the wind is too strong, causing the rotor to spin too fast, for example, reaching 1600 RPM, the output frequency would become 53.3 Hz. The controller then generates a reverse negative value to subtract the excess 3.3 Hz, bringing it back to 50 Hz. So, it acts like a precise frequency tuner, ensuring the frequency delivered to the grid always remains stable at the standard 50 Hz. Now, the electricity generated within the nacelle has stabilized, allowing it to be transmitted down the tower to the ground. Specialized cables will then carry this current from the nearly 100-meter high nacelle all the way down to the tower's base. At the tower's base, transformers are installed. The voltage produced by the generator is typically only 690 volts, which is enough for local consumption. However, for long-distance transmission across the country, such low voltage would lose most of its power during the process. The transformer's purpose is to boost voltage to 35 kilovolts or even higher. The boosted current then travels through underground cables, collects at substations, eventually joining the power grid, and is distributed to countless homes.